Hi folks, Mr. Long here. I'm going to go through and develop what's called the Fundamental Theorem of Calculus, Part 1. I'm going to develop it conceptually. Excuse me, and we're going to go back. And what we're going to do is go back to these silly snowfall graphs and look at snow accumulating versus snow melting and those sorts of things. So what we can do here is take a look at this graph, and let's just, first thing my eyes go to is a graph if it's in a question, right? And so I'm looking at the graph and I'm wondering, what does the graph show? What are the units? Is it a rate graph? Is it an original function? What sorts of things? So, and what are the units on the x-axis? What do they represent? So that's the first thing I look at carefully. So I'd be looking right there, right, at the fact that the units are centimeters per hour. So I know I've got a rate graph. And then the time is being measured after 8 a.m. And I would also say that this f of t is always positive, okay? The y value is always positive all along here, right? All along there, that's positive. It's always snowing at a rate of 3 centimeters per hour. So the snow is, if I'm going forwards in time, right, from 0 to 1 to 2 to 3 to 4, then definitely the snow is accumulating on the ground and the snow is getting deeper. What I don't know here is how deep the snow is until I start to read the information in the question. Okay, so what that means, by the way, is t equals 0 is at 8 a.m. Okay, that's because it's hours after 8 a.m. Okay, so let's look at what the actual question says. If the snow was 40 centimeters deep at 10 a.m., how deep was the snow at 8 a.m. and at 1 p.m.? So we've got to connect this to how we were representing the x-axis, which is time after 8 a.m. So 8 a.m. is t equals 0. 10 a.m. is then 2 hours later, so t equals 2. 1 p.m. would be, so 9, 10, 11, 12, 1, that's t equals 5. Okay, hours after 8 a.m. So I need to figure out how deep the snow is at 8 a.m. and at 1 p.m. And one thing I do know is there's 40 centimeters of snow at 10 a.m. So I'm going to go over here to this graph. Now, can I plot that 40 centimeters on that graph? Does it make sense? No, it doesn't. Absolutely not, because that 40 centimeters is from an original function. That's the depth of snow. That's not the rate. Nonetheless, I'm going to put this right here. I'm going to circle that 2, because we know at 2 hours there are 40 centimeters of snow on the ground. Here's the part that I hope you're listening to. Actually, I hope you listen to all of it. But here's an important piece. Where was the snow deeper? At 0 hours or at 5 hours? If it was snowing 3 centimeters an hour the whole time? Well, pretty obviously the snow was deepest at 5 hours, because it continued to snow throughout those 5 hours. Okay, t equals 5. So that means the snow's less deep at 0. Okay, but we know there's 40 centimeters. So that's it. That's actually, that 40 centimeters is from the original function, not the rate. So that would be big F. Okay, so let's take a look and let's do this one here, the 8 a.m. one. Okay, so we're going to get how deep the snow is at 8 a.m. So when we go over to here, we have to, of course, do our area under the curve. Right, there's our area under the curve right there. And this is the area I'm interested in, because I'm trying to figure out, remember this is 8 a.m., that's 10 a.m., right? So I'm trying to figure out how much snow accumulated between 0 and 2 hours. So this right here is the delta y. That's how much y I'm going to multiply by, and this is how much x changed by over that time. Okay, so now what I need to think through is I'm going backwards in time. I'm starting at 2 hours and I'm going back to 0 hours. And that's a little confusing. So delta x actually is going to be negative. And remember, there's going to be far less snow at 0 hours than there are at 2 hours, because it was snowing the whole time, right? So when I'm doing these with, like, not with formulas, things will take care of itself when you're working with algebraic functions, but when you're working with these diagrams, with pictures like graphs, when you're working with just graphs without algebra, you really have to be conscious of, is delta x positive, negative, is delta y positive or negative. So this right here represents our y value. It's not changing, and it's positive. So delta y is definitely positive, but delta x in this case, I'm going from 2 hours to 0 hours, right? Because I know I'm 40 centimeters at 2. Everything's relative to this 2-hour mark, because that's where I know I've got 40 centimeters. So delta x, I'm going from 10 a.m. to 8 a.m. So is delta x positive or negative? And we know it's 2 hours. It's actually negative because I'm going backwards in time from 10 to 8. Delta y is a positive. So 3 centimeters an hour. And then to get that, we just get area. And I should actually put my negative here as well. So I have the A1, which is, I'll call this area here. Oops, that's A1. Okay, that's A1. And A1 is going to be delta x multiplied by delta y, because it's a simple rectangle. Negative 2 hours because I went from 2 hours back to 0. I went left. And then the 3 centimeters per hour, that's the y value. Okay, so I just multiply that out and I get 6 centimeters. But it should be negative 6 centimeters going in that direction. What does that actually mean? From 0. So this is actually from t equals, I should actually correct that, because that's going backwards in time, right? That's going from 2 hours to 0 hours, right? So the question is, and would it make sense then? So if I know the snow is 40 centimeters deep right here after 2 hours, was the snow less deep at 0 hours or more deep? And I think it's pretty intuitive that it's less deep, because if you're standing out in a storm, if you walk out in a storm and the snow is at 0 hours, say, is up to your knees, the longer you stand outside, the snow is going to go up higher and higher, right? So if you look back in time, there's going to be less snow, right? There's going to be less snow. So that's why this is a negative. That's a negative accumulation of snow, because I'm looking back in time. Okay, delta x is negative. So was the snow deeper at 8 a.m. or 10 a.m.? For sure. Oh, snow was, sorry, that's not the case. At 10 a.m. it was much deeper because it was snowing for 2 hours. Okay, so let's do the depth at 8 a.m. And the depth at 8 a.m. is that doesn't look very good, does it? The depth at 8 a.m. is the 40 centimeters at 10 a.m. plus the accumulation 10 a.m. to 8 a.m. Right? So that's 40 centimeters deep at 10 a.m. And then we've got to add on negative 6 centimeters. Why is it a negative? Because the snow is less deep. Okay, at 8 a.m. there's less snow. There has to be, right? Because it was snowing. It was accumulating from, if you look at it from 0 to 2, it accumulated. So you can think of it, if you're looking backwards in time, it actually is like melting off snow, right? Because you're going back to the start of the storm before the snow accumulated. And the overall depth is then, is 34 centimeters at 8 a.m. Okay. All right, so now let's look at it. That's the hard one, by the way. Now we're going to try and figure out the depth at 1 p.m. So in this case, I'm going forwards in time, right? I start at 2 hours, and I'm going to look at how much snow accumulated from 2 to 5, right? I had to look at 2 to 0 before. So I'm going from 2 all the way to 5. So to me, that looks like a delta x of 3 centimeters per hour, or sorry, 3 hours, sorry, from 2 to 5. And so from 2 hours to 5 hours is 3 hours, and we're going to the right, so that's positive. 5 minus 2 is 3. And then we also know that the snow is coming down at a rate of 3 centimeters per hour. So again, this is A2 over here, right? This would be A2 there. And we can see it's a square, right? 3 centimeters tall, 3 centimeters per hour tall by 3 hours wide. And the hours will cancel out when I multiply. I'm just left with centimeters. So 9 centimeters of snow accumulated or fell on the ground between 2 and 5. Okay, t equals 2 and t equals 5. So what's the new depth then at 5? Well, the depth at 1 p.m. is the 40 centimeters. By the way, stop, pause, go back, you know, maybe do some calculations yourself, right? You should be working through these examples. Sorry, I'm just drinking a tea right now while I'm going through this. So 40 centimeters of snow at 10 a.m. and then 9 centimeters accumulated from t equals 2 to 5 hours. Okay, that's the accumulation, is the 9, and we started with a depth of 40. So, and it fell all that time, and we're going left to right, so delta x was positive and delta y was positive. So that's going to be 49 centimeters. Okay, so that's looking at it intuitively. Okay, intuitively. So it's basically just an initial value for the original function plus the accumulation. You can see that right here, right? So we can see we were trying to figure out an unknown y value in the original, which is, for example, the depth after 5 hours. We have to know a y value on the original. We did, 40 centimeters. And I know that's on the original function, not on the rate, because it's being measured in centimeters, not centimeters per hour. So 40 centimeters is not a rate. Okay, and then, so that's the known value. And then I accumulate all the way from x equals a to x equals b. Right, and that's, again, this is a tough concept. It's clearly important because otherwise the folks that started this whole field wouldn't have called it a fundamental theorem. Okay, so take your time, make sure you start to understand it. Okay, so that's the conceptual framework for the fundamental theorem of calculus part 1. In the next video, we're going to take what we have right here and put it into calculus notation. Okay? Take care.